But they just called me. I didn't contact anyone. I didn't press charges. I didn't do anything. I just want to.
There's this trick
Yeah.
that fellows
They called me.
give a nice call.
Send me letter.
colleague of ours. She's passing through State College over the weekend.
Yeah, otherwise she would have just kind of been headed through Pennsylvania, but unfortunately, somewhere near Akron, Ohio, she
I see.
Need, so.
I see.
Looking forward to you talking.
Yeah, thank you. Yeah, it's good to finally connect name to a face. Yeah.
No, in all that.
I believe that.
I come to.
Yeah.
So it's called colloquium on the website. Are you expecting like a really colloquial?
Colloquium mean actually? Colloquium means bigger crowd.
I usually see it's bigger crowd, more diverse
I see.
community, symbolized by the focus on small groups.
I was thinking of a seminar, so I was gearing towards a seminar.
You guys done any graphene devices without encapsulation?
Without encapsulation?
Very old way of thinking.
No.
I see that this is
Not personally.
Did it 10 years ago.
Yeah.
Nobody could do that.
well, after measure, you can
No, we don't.
you'll save that.
We almost never remeasure
Yeah.
things, right? It's just in the door somewhere, but it feels good to have it.
You want to see non-hydrodynamics. Make a device, no
Is that
hydrodynamics.
right? You hold it all the way from the I see. Some of my
It's supposed to be like that.
Miscommunication. Anyway, I'm I mean, we probably have. Yeah, chips, just graphene, so you grab silicon oxide, you just put contents on it. It's easy.
One didn't work out so well.
I don't know if it's gonna be the day. I just try a few things with Frank.
3 out of 7 contacts are working.
We are colleagues. We are not friends. Contact.
So with some
So maybe.
Quite a lot.
Okay, let's start. For a few more minutes.
Oh,
We get rid of our 7 minutes now.
I'll give it 5. I
5
think
minutes,
starting
okay,
to
now we're
mention
just
it.
waiting.
Why is it there's a universal 5 minutes rule everywhere?
Usually 7 minutes.
It was an official policy that there was Harvard time. So like things were scheduled, like classes and things were scheduled like over, like, you know, one class ends at 1:30, next class starts at 1:30. But it was just understood that you had 7 minutes to get there. So like the classes would all start 7 minutes late.
But then we get rid of that.
But yeah, that's been
we have the
abolished.
15 minutes gap supposedly. So we should start and sharp.
45 for all.
Yeah, there it is.
So we give it 15 minutes. Bob is right. We should have wait time because the more people
Exactly, actually, they're all observing this. It's messing up by scheduling big classes back to back with no travel time. So you get students crossways in and out, and you've seen our very steep classroom, right?
I'm not sure how much those.
I'm assuming you
No, Mary's interested. Just talking about it.
yeah, the scanning gate. No, we're finished.
You're doing it. Yes.
We already did. Just need to review. Pass.
But you need to show that it's dynamic. Well, you're not in that really.
Yeah, obviously when
It's my great pleasure to have Professor Junju from Penn State University. Jun did her bachelor's degree in Japan to China, USDC, and then came to Columbia University for her PhD, working with Holstormer. And I believe you're the Holstormer's first students ever, right?
That's right, yeah.
That's right.
Oh.
Initially first student. Yeah. He didn't produce many PhDs, but
And after PhD at Columbia, she went to the Cornell to postdoc work with Paul McQueen. And 2006. Right, okay, so 2006 she came to Penn State and started her career there. And since then she's been there and doing a lot of great work. And especially, I think quite recently, this the realization of valleytronics in graphene. It's a very exciting and interesting development. Probably able to hear today.
well, thanks Philip for the invitation and the kind introduction. So Philip and I go way back because Philip started at Columbia around 2000, 2001-ish, and used to come to our lab to borrow stuff all the time. So, and we were both postdocs at, I guess you were at Berkeley, right, with Paul, so we didn't overlap in time. Anyway, so I'm going to tell you a story about Bilayer Graphene. This is something that we work on a lot at Penn State. I'm going to talk about how you make valleytronics devices. And the word topological valleytronics is important. It turns out if you don't use topology, it's actually very hard, almost impossible to make a valleytronic. So I'll explain as I go what I mean by topological. So, but I want to step back a little bit and just sort of pose even a bigger question, which is how do you wire up a quantum computer? Right? So we know how we wire up a classical computer. So we use layers of interconnects. Right? These are made of copper these days. It was invented by IBM back 22 years ago. Right? So this is a processor. You're really looking at just the copper interconnects there, right? Very sophisticated network that connects the bits together. And there are 15 layers of them. Right? Okay, so fast forward 20 years. This was also IBM, 2017. And that is a 7-qubit quantum computer. Right? So it's nicely color-coded. Each one of them has its own coplanar waveguide. Right? Okay, so you got can you imagine a communication network where everyone has their own telephone line? Right? So we're all, clearly, we don't have a scalable way of wiring up quantum computer, not yet. Okay? So and in order to do that, you'd have to come up with some sort of a quantum interconnect that we want to transport your information, electrons or not, ballistically, that means without incurring dissipation, also coherently. Right? So that's because we're doing quantum computing. We want to maintain the entanglement and so on and so forth. So we're not there yet, but today I'm going to focus on the first aspect of it, how to make ballistic quantum wires that could perhaps one day maybe connect your qubits together. Okay. So how do you do that? Right? How do you make electrons move without incurring resistance? Well, you can already gain a lot by working with lower dimensions. Right? That's kind of easy to understand, right? If you're working a two-dimensional plane, you have many more angles to scatter, to collide with. If you reduce that to a one-dimensional world, you're doing a lot better because your phase space of scattering is reduced. Right? So by saying the word wire, you are already gaining quite a bit. Right? You can make wires either by growing them in materials or lithographically pattern them from a two-dimensional sheet. But this is it doesn't completely solve your problem yet, because you can still have head-on collisions even if you are traveling on the road, right? So long as your cars moving in opposite directions have the chance to collide with each other, this will happen. So electrons can be backscattered in a one-dimensional world as well. Right? And you do a lot better if you make roads that are chiral, meaning cars or electrons travel in one direction are physically separated from the opposite lane, right? A lot harder to have a head-on collision in this case, right? Okay. So in solid-state systems, we have such wires, and those wires are the edge states of what's known as the quantum Hall effect. Right? Okay, so here's my one slide introduction on what is the quantum Hall effect and the chiral edge states. Right? So we all know the classical Hall effect. You have a 2D sheet of electrons. You put a magnetic field perpendicular through the plane. Electrons in the holes feel the Lorentz force. They bend opposite towards opposite side of your sample, and there is a Hall voltage across the sample. Okay. So now you start cranking up the magnetic field. The cyclotron orbit gets smaller and smaller. At some point, some of the electrons are making full circles inside your sample, like what's shown here. Now, intuitively, you can already see that these electrons aren't participating in conduction from source to drain anymore because they're just running in circles on the spot. Right? But they have these skipping orbitals that bounce around the edge that's actually carrying the current between the source and drain. Okay? So that's a semi-classical picture. The quantum mechanical picture of quantum Hall effect goes like this. So this middle develops the bulk of the sample, develops what's called the Landau levels, and they are gapped. So no states in the bulk. Right? This is a gap. Now your sample ends somewhere, so the potential has to go up. Right? So when the Fermi level crosses these potentials that go up, you have what looks like wires, right, go in and out. So these are quantum mechanical version of these skipping orbitals that I just drew there. Right? In fact, the way that I'm plotting it, this is space, but it also can be momentum. It's introductory quantum mechanics. So this is energy versus momentum. That's a dispersion relation. The slope of it is the group velocity of the wire, right? So you can already see that on the two sides of the sample, the wires counter-propagating. They have opposite group velocities. So like what I'm showing here, the one on top goes this way, the one on the bottom goes an opposite way. Right? So now if I don't apply a bias between these two, the current carried by this guy and that guy would just exactly cancel each other. Right? So you get zero current. Now, in order to get a net current through the device, you have to, let's say, give this edge more electrons. So you bias the source a little bit differently. And then if you work it out, how much voltage you have to apply in order to get a certain current, the conductance of the system is such that it's always an integer multiple of E squared over H. And that prefactor in front, nu, is the number of counter-propagating states you have. So the way that I'm drawing it here, I have one pair of counter-propagating edge states. I have 1 E squared over H, and that's a quantized conductance. Right? Okay, so this is a very robust system, just like the divided highway I'm showing you, because for an electron to scatter from this edge to the other edge, so long as you have no states in the middle that could make this one hop all the way to here, then the electron has no way to go. This is, remember, there is a gap in the bulk here. There are no states the electron could use to connect to the other edge. So the robustness of a chiral edge state of the quantum Hall effect comes from this spatial separation, which is your best friend, basically, in terms of protecting that ballistic transport. So in fact, it is so robust, this unit of quantization, E squared over H or H over E squared, is your resistance standard. It's called the von Klitzing constant. And all the experimentalists should know this is 25.8 kilo ohms, right? So if your advisor asks you to compute, you want to compute on the spot, right? So this is, we can do precisely measurement of that number to this many digits. In fact, it's so precise these days, even the mass is defined by balancing electrostatic force with gravitational force. So the mass standard is no longer this is a platinum sphere in Paris, but rather defined by the von Klitzing constant. Okay, so this is all very good, except one thing. right? One caveat. You see, I have made a loop here for my current, right? How did I do that? So I broke time reversal symmetry by applying a magnetic field. Right? By inverse field, it goes the other way. Right? So there might be cases where you don't want a magnetic field. Then quantum Hall effect doesn't happen. Right? So then what do we have in order to create ballistic wires to prevent that backscattering from happening? Right? Can we do this preferably at zero magnetic field? Right? Got to think of other tricks. So I have a very contrived situation here. Suppose I paint the road. Right? I paint this lane blue, and I paint this lane red, and I say blue cars go that way, red cars go that way. And then I say if you want to crossover, you have to change your color. Okay. So in order for electron to backscatter, it needs to change something else. That color is some other degree of freedom of the electron that I now link to the direction it travels. And if I can get rid of all the places where the color change can happen, then I could prevent an electron from going from here to here, right? Okay. So that color degree of freedom could be spin. And then we would have spin momentum locked wires, quantum wires, right? Okay. Such system actually exists. So spin momentum locked quantum wires are edge states of what's known as two-dimensional topological insulators or quantum spin Hall effect. Now, how many people work on that here? No? Nobody? Oh, okay, a little bit. So I think Mir Jacobi's group does quite some nice work on this in this regime, right? So the way it happened is it's a strong spin-orbit coupling material. And because of that spin-orbit coupling, there's a piece of the conduction band, let's say the S-like band, the orange color, that ended up in the valence band, and a piece of the PU-like orbitals ended up in the conduction band. So if you look at in the momentum space around that place, it looks like the gap inverted itself. There's some sort of band inversion that takes place. Now, this is my sample. My sample ends somewhere at the surface of the sample, right? Okay. So when it connects to vacuum looks like this. Your quantum mechanics tells you your wave function has to be continuous. So for a wave function that has this kind of symmetry to go and connect with this place over here, you realize if this gap is finite, that tunneling process will not happen. So in order to connect the wave function from here to here, this gap must close at the surface of the sample. And that's the reason we have gapless edge states at the surface of a topological insulator. When that topological insulator is a 2D system, the surface of that, boundary of that are edge states. So these edge states are spin momentum locked because the way they come from spin orbit coupling. And you can see over here, indeed, that's the case. So if I look at spin up, it's going one way, spin down, it's going the other way. On the other side of the sample, it's doing the opposite thing. So if I'm looking at spin up, it's forming a loop this way. If I'm looking at spin down, it's forming a loop that way. See, I did not break time reversal symmetry in this case, right? So I have two sets of counterpropagating edges on the side of the sample. Okay, all right, so, oops. Usually I ask the question, what is the conductance of the system, just to make sure you guys are awake. But I think I gave this answer away down here already. Right? We get 2e squared over h because we have two pairs of counterpropagating states. Right? So if you put a contact here, put a contact there, you measure 2e squared over h, provided there is no scatter that could connect this state to that state. And that requires a spin flip. So naively, you might think, if I get rid of all the magnetic impurities of my system, then I could suppress that backscattering and have ballistic conduction. Right? So that was indeed the hope. And how is it working so far? So it's working somewhat, but not too well, actually. So starting from 2007 or so, so this is 12 years in, and we have starting from the first topological insulator system, cadmium telluride, merc telluride, cadmium telluride, to other candidates these days. A lot of them are in 2D systems over here. 1T prime, WT2 is probably the latest addition to that. People from the center work on these materials, one of your thrusts. But if you look at what everybody has got so far, the conductance quantization isn't really so robust. Okay? You have to work with low temperature. Is it quantized? Maybe, not quite, right? You do a log plot. So we do log plot in order to hide fluctuations. Right? So it's not really that robust. Right? This one, it's pretty far away from what you might expect, right? Short mean-free paths. What's going on, right? These systems don't have magnetic impurities, but yet we're seeing some backscattering. So some of the thoughts, and this is something that's ongoing, is the gap is very small in these materials. So we're relying on spin-orbit coupling to invert that gap. And typically, we're looking at something on the order of 10 millieV or so. And all of these materials are not so easy to make very pure, actually. So you have impurity states. Impurity states sometimes live inside the gap, sometimes live very close to the band edge over there. So the structure near these gapless states that we want to look at is actually fairly messy. So there are processes that could lead a spin flip from this guy to this guy, maybe have the nearby impurity state also flip its spin, sort of a higher order scattering process, right? If you have lots of them, it would add up and give you a sizable resistance. Right? So I guess what I'm saying over here is that it is really not so easy to make robust ballistic transport for these helical states where the wave functions are on top of each other, right? And it's much easier if you physically cipher them, turn them into chiral, right? But we work with what we have. So working with what we have here, if you look at this diagram here, some thoughts is, it would be nice to have a large band gap, right? And then it would be nice to remove all the states, all the in-gap states. So it would be nice to put the gapless edges that you want to study into an empty box, as empty as possible, as big as possible, as far away from any trivial states it could interact with as much as possible. And then it would be more robust, right? Okay. So how do we do that? Right? Maybe looking at a new material system is not a bad idea, right? So today I want to tell you about a system that's based on Bilayer Graphene. We're using sort of a similar rule here. So we're playing this color, this new degree of freedom. And instead of being spin, my new degree of freedom, my color is valley. So valley is something that two-dimensional hexagonal lattice crystals have a new degree of freedom. It's in the momentum space, as you will see. And I want to show you sort of these creation of these valley momentum locked wires, okay? And show you what it looks like, what it does in terms of conductance. We are getting close to 4e squared over h, not quite yet. And you will see, in fact, one could play some really cool experiments on the system by using gates to direct where the edge states would travel. So some tunability in terms of control. And these go under sort of these, you gotta give it some function, right? So I say I made a topological valley valve. Right? Topological is the keyword. And I made a tunable electron beam splitter where I could control how much of this coming in, how much goes to the left, and how much goes to the right. Right? Okay. So that's the plan. Okay, so it starts with graphene. So you probably have seen the slides or something like that 100 times now. Okay. So the thing important is we have two valleys, K and K prime. So K and K prime, the orbitals that thread through K and K prime are pi and pi star, because the way that they thread through this point is a bit different. You can see that here the blue is to the left of the red. Here the blue is to the right of the red. And if you reduce that, all this band structure to a low energy Hamiltonian, just looking at that point, the Hamiltonian looks different for K and K prime. So the physics is different. There's a minus sign in front of one of the valleys. Right? Okay. So that tells you there's some valley contrasting properties that would occur in this system. Right? They're both cones, but they're not identical cones. So this system has no gap because there is an inversion symmetry between the sublattice A and sublattice B. They're both carbon atoms, so that gives you this touching point in the dispersion. Now, if you break that symmetry, for example, I put B here, and then I put N here, hexagonal brown nitride. Everybody knows it has a large gap. Right? That gap comes from breaking this sublattice inversion symmetry. Now, there are other ways of doing so with transition metal dichochronites, such as moly disulfide, tungsten diselenide, which share the same symmetry and the symmetry breaking of that gap. So when the band gap opens, we can see a lot of valley contrasting properties a little more clearly than graphene, actually. One of them is orbital magnetic moment, and this is something you probably have heard in the context of looking at the valley contrasting properties of TMDs. Right? So orbital magnetic moment points in opposite directions in K and K prime, and together with the spin-orbit coupling, it gives rises to bands that carry different spins in K and K prime. Right? So that's something. Another thing that's very contrasting is the Bilayer curvature, something that characterizes the vorticity of the momentum space wave functions. And I'll come back to that. Right. So a little more on this, my control is kind of lagging behind. A little more on this valley sort of tronic idea. Right. So this is a semiconductor with a band gap. So I spoke of the contrasting orbital moment and then spin-orbit coupling that give rise to these opposite spins in different valleys. There's also, you can work out the selection rules for these optical transitions. And then you realize that one valley couples to light of one-handedness, and the other valley couples to light of the opposite-handedness. So one can effectively pump the population of one valley by just selecting the handedness of your light. Right? So Opto-valleytronics works. Right? Okay. Spin-valleytronics also works because there's the induced spin momentum blocking. A lot of the work in TMD materials have gone in these directions to try to utilize these two connections to make some sort of a device out. Right? It's quantum, not quantum, Valley Hall effect. Here's a nice work that shows the optical spin injection through the TMD. Right? But it's actually hard to do electronic valleytronics. Right? If you think about it, you're looking at two momentum K and minus K. Normally, if you don't do anything, they're equally populated, right? So you don't have a net valley polarization. There are experiments that try to create that by using something called a Valley Hall and then detect that by inverse effect. But we're talking about a very small fraction of the electrons near the Fermi level in those cases. So the valley polarization is tiny. It's good to look at science. It's not going to be useful in a device by any means. Right? And I wish I had a valley magnet, or just like a magnet. You just put it on the sample and inject carriers with a particular valley polarization. Right? It's hard enough for spintronics, but at least you have a magnet. Here we don't have something called a valley magnet. Right? Right. Right. So is it really hopeless? Okay. So I wouldn't be here if it's completely hopeless. So I want to tell you how you can actually use topology to get around the game of you can't really create an appreciable valley polarization very easily through electrical means. Right? Okay. Keep that in mind. Okay, so the material we work with is Bilayer graphene. That is Bernal stacked Bilayer graphene. So before the twisted Bilayer graphene came out, I say Bilayer graphene, everybody understands what I talk about. Now I say Bilayer graphene, everybody says, what angle are you twisting? So this is not twisted. This is just straight Bernal stacked Bilayer graphene. It comes out so from a graphite crystal, and it looks like this on silicon dioxide. Right? Okay. This is a side view of how the atoms stack on top of one another. It's top layer, bottom layer. And there's one set of atoms that stack right on top. So the on-site interaction is strong, and that forms these high energy bands that are lifted away from the Fermi level. These two guys, B1, A2, looks just like the sublattices of monolayer graphene, right? So that symmetry is still there, and that gives you these quadratic touching bands at the Fermi level, right? So that's what pristine bilayer looks like. The very nice thing about the system is that you can break that inversion symmetry very easily in bilayer graphene. Not so much in monolayer. Right? So you see, if I apply a perpendicular electric field through my sheets, I give B1 and A2 different electrostatic potentials, right? So the lower energy goes here, the higher energy goes here. So my top and valence band, my top of the valence band and bottom of the conduction band are now split in energy, and they correspond to either B1 over whichever way is lower energy, and then the other one is the other site, right? So this gap that I opened by putting an electric field through the sheet is proportional to E, right? Quite straightforwardly. And really, it's very nice if you think about it. To invert this band gap, all I have to do is change the direction of E. Then I will have inverted the potential of those two atoms, and then I will have inverted my band bottoms, right? Right. So that is really, it's really hard to do so in a monolayer graphene, right? So how do you break that symmetry and how do you invert that symmetry? So this is something that we are very happy to see. The second nice thing about bilayer graphene is we can open a band gap as large as about 200 millieV in these BN sandwiched geometries. Right? Well, 200 is very nice compared to 10. Right? So remember what I said before. We want to put our valley momentum locked states inside an empty box. So having a larger gap is something that would help you keep the states more robust, right? So and you can see indeed the gap comes up almost linearly with the applied displacement field, right? Okay.
So this gap was measured by the activation of the transport? Or?
Yeah, it's in the supplementary material of this paper. Right. Our early measurements in 2010, we saw a lot of disorder. And then in cleaner samples, we saw nice activation. But the physics didn't change, so we didn't bother to write anything. It's in the supplementary material there. Anyway, OK. So here came a proposal that was about 11 years ago now by Ivar Martin and colleagues. They say, why don't you stick these positive gap and negative gap regions together in a way that I draw here. With a pair of gates, I'm gapping the left. Another pair of gates, I gap the right. I put opposite field on, so I'm getting plus and minus gap. And because of that band inversion, just like quantum spin Hall systems, I expect gapless modes right in the middle of the junction, right? The zero energy modes. Okay. So of course, it goes a little more complicated than that. You can look at the calculations if you're interested. But at the end of the day, we expect 4 pairs of modes. And I'll explain in a second where 4 comes from. They are valley momentum locked. So K and K prime propagate in opposite directions with opposite group velocities. Right? That's a helical system. And their wave functions live inside the junction. They're on top of each other. This is an actual simulation. So they have a few tens of nanometers of width. Right? So your quantum wires live inside this electrically created line junction between a positively gapped and a negatively gapped area in Bilayer graphene. So we call them kink modes, kink states. And that's it's actually similar physics was seen before, even in the 1970s. I don't know how many people know about solitons in polyacetylene, polymer, yeah, right? You're certainly old enough, Bob, to know that. Right, so those are called the kinks, right? If you look at it, this is alternating double and single bonds. That's the gap mechanism, right? And then, whoops, here's a phase slip of some sort. It goes double, single, single, double, right? So plus gap, minus gap. There's a conducting state there. And if you chain these polymers together, form a network, it actually conducts through these solitons. Okay? And the states live inside the band gap. This is very early calculations, and they look like so. Okay. So that's so we call our stuff kink states also. It's in the middle of the sample, not the edge of the sample. It's internal. Okay. Actually, you can also create this in Bilayer graphene by playing a game of finding a domain wall. Right? All I wanted to do is reverting the sign of the band gap. I can do so by changing electric field, or I can do so by changing the stacking order. This is AB, this is BA, apply the same electric field, but my potential has swapped, right? So if you find one such AB, BA stacked boundaries, you have yourself a domain wall mode that shares the same physics. In fact, this was the first experiment in a system like this was done by looking for such domain walls in natural graphite. Just look for ABBA domain walls. Yeah?
When we say it's very momentum protected, like if, let's say along these edges you have some disturbance, right? That has delta K, which is like K prime minus K. That's not enough?
It is enough. If you have an atomic defect, you would scatter from K to K prime.
It has to be clean.
It has to be clean. And thanks for that question, because graphene is very clean. Graphene doesn't have atomic defects. So in fact, this is something that Elie Zeldorf did to show what is the density of defects in graphene. It's very, very low. You wouldn't find one in maybe in a 10 micron by 10 micron square. There's no defect, right? So that's a good thing, right? So that's something that we rely on, right? So that's the first experiment. And then after this twisted Bilayer graphene came through, I know you guys are trying really hard to make these samples, right? So if you didn't get the magic angle, you got a small angle. The sheet will relax itself into a network of these domains, lo and behold, with domain boundaries in between AB and BA. So you get a network of it. This is, Philip, you recognize this, right? So this is work from Philip's lab. They're imaging the sort of these domains on a TEM and looking at transport across the domains. There are other measurements that looks at plasmonics propagation in this network of domain wall modes. There are other measurements that look at coherence behavior in the magnetic field. This is probably not a complete list of things, but we wanted to electrically control it. And we want to work with one or two or a few of these, right? So we decided to go about it the harder way, which is using the gates. So for the theorists in the audience, why do I get 4, right? And what sort of is this thing topological, right? So the kink states come about because of some topological states always come about because some topological invariant changed its number. Right? So here, this topological invariant is the difference of the Valley Cher number across that line junction. Now, I mentioned that there are Valley contrasting properties. One of them is Berry curvature. If you integrate the Berry curvature in the entire momentum space, you get a Cher number. Trivial insulator has a Cher number of 0, right? Okay. So you can also integrate it around one valley. So in graphene systems, when you do that, in bilayer graphene, in K valley, you get a plus sign, and in the K prime valley, the minus K valley, you get a minus sign. Right? Now, if you change the sign of the band gap, those two numbers also flip their signs. So if you look across this line boundary, the change of the Cher number in the K valley, it's +2. And in the K prime valley, it's -2. It's a non-zero number, which means you have an edge state corresponding to that. So this is the origin of these counter-propagating edge modes at the line junction. Right? So you get 2 from that number, and then multiply 2 for spin. Because I haven't talked about spin at all. Spin is not an actor in all the physics that I'm going to talk about, right? So we have 4 pairs of counter-propagating modes living inside the junction. So what is the 2-terminal conductance, guys? If you hook up the 2 electrodes and measure?
2 square over h.
Come on, say it. 4e square over h. Thank you, because I have 4 pairs of counter-propagating modes, right? I expect 4e square over h if there is no backscattering between k and k prime, and atomic impurities can cause k to k prime backscatterings. And other things that are inside the gap, higher order scattering process, could also do that. So the game is similar to what quantum spin Hall system need to play. Make it clean, make it as clean as possible, and make the gap as large as possible to suppress those processes. Right? But we start with a very clean graphene so that we don't have atomic impurities. Right? And in case you're curious, it's protected by time reversal plus a mirror symmetry. And as I mentioned before, we are creating this inside the bilayer graphene sheet, not at the edge. So that's good, because edge tends to be more disordered. Right here, I'm not touching the graphene lattice. It's all electrically defined. Right?
Is it mirror symmetry or inversion symmetry?
Ah?
Is it mirror symmetry or inversion symmetry?
A mirror.
But bilayer doesn't have mirror symmetry. Mirror, what is mirror?
Here.
So actually it's for
Yeah,
the
right,
back.
right, right, right. So, and this is the reason why you turn on magnetic field, it's still there. Because it's the two of them, not just time reversal, right? And you will see me using a magnetic field, right? Yeah?
In the devices you guys make, how do you know there's no natural domain?
Oh, very good question. So at some point we looked. Out of 10 pieces, sometimes we would see a little thing, maybe here. It's very rare in our pieces. What we can tell experimentally is if we are so unlucky we happen to go across one, we point our field in the same direction, we should see it. When we point our field in the opposite direction, we shouldn't, right? Because it inverses itself. We never saw such thing. So in all our bilayer graphene devices, if we don't intentionally create this, we see insulating behavior inside the gap. So we haven't hit on one of these by accident yet. But it does exist, and that's how Longji did his work, right? He went and looked for those and worked on those, right? Okay, so this is the structure of the device. We have 5 gates, so a pair here, a pair here. We're gapping here, put it in a charge neutrality point, gapping here. We're using this gate to control the Fermi level inside the junction. Right? Okay, so that's what the potential looks like. This is a calculation by my colleague Zhenhua Qiao. that again shows the chiral modes in each valley, helical all together. But you can also see some modes that encroaching into the band gap. And those are the modes that live inside what I call the nanoribbon. So my line junction has a finite width. It supports modes that just live inside that width. And because it's a finite width, and it's about 60, 70 nanometers, those modes start here and here. So I have a band gap of about half of what's in the bulk to work with. That's really what's confining the kink states. Okay. So a lot of this field came about because the wonderful people at Columbia, Philip and Jim Hong, worked hard to make these very clean devices, right? The van der Waals heterostructures. Yes?
In the previous slide, you said the width of the channel is about 16 nanometers.
Correct.
So how is it important to have 16 nanometers? So he also mentioned about like atomic defects. Do you really care about this width?
Yes, you want to make it as narrow as possible. If you make it really narrow, you push these blue states down, and you have a larger gap to work with, and you were limited by lithography, right? It doesn't have to do with atomic defects whatsoever, because that's not relevant, but it has to do with how far can you push the lithography.
Basically, you're trying to make this narrow as
Correct, yeah. If you make it a 1 micron junction, these blue states are going to come in and almost touch 0. Then we're back to 10 millieV, and very small gap, right? Right. So in theory it works, but in experiments it doesn't if it's too wide. Yeah.
You think resist residues and stuff like that? Like you think resist residues and stuff like that exactly between the gates effect, or
It probably is a very weak form of disorder. This is a silicon gate. I think that's our biggest problem in terms of quality, right? So the thing we're doing now is to change everything to graphite. And then maybe at some point we would start worrying about resist. But resist so far, it hasn't bothered planar devices at this level before, right?
You also want to use a thick boronite, right? So that the disorder is smoothed out in the graphene channel. Is that correct?
To some degree. Once you are too thick, you start losing the control of the electrostatics. Remember what I said about simulating? So we did do some simulation, right? You don't want it to be too thick. Right? Yeah?
how about alignment between two pairs of gates?
I'm getting there. Right. Okay. All right. Very good. Very good questions, guys. Right. Okay. So we learned from the masters on how to stack these things. Right. Philip can stack 7 layers of this together and get wonderful exciton condensate out of it. We thought we can't compete with them on that. Let's try to make very small devices in the lateral direction. Right. So that's the direction that we pursued, which is to have this lateral complexity. Right? So I'm going to show you 2 kinds of devices. So our first generation, it's wet transfer for those of you who know what it means. We put down graphite. We etch a split out of it. This is RAE. We put down hexagonal brown nitride. We put down bilayer graphene. We etch it into a whole bar. We put down hexagonal brown nitride. We do contacts, and then we pattern our top gate. Right? Okay. So when things work, it took a few years to get that stage. They look like this. Right? Okay. So this is a color, false color SEM image. The purple stuff is that graphene. Right? This is the top gate. The big black square is the 2 graphite back gate. And this is the top HBN that you're looking at, right? So we go current in and then voltage from here to here. We measure transport across that junction, right? Okay. So we got a little more ambitious. We said, okay, let's make a 9-gate device. Yes?
Graphite doesn't, like when you etch and you put after that, graphite doesn't move, it stays fixed.
It stays
Even
fixed.
though it's very small.
It's 3 nanometers. It's not that thin.
No, I mean like it doesn't show suddenly.
No, it doesn't. No, it doesn't. Right? It's very robust. Yeah. So we, our second generation, we had a 9-gate device. The difference here is instead of 2 pairs of split gate. We have 4 pairs that form this cross. Okay? So the way we look at the cross is if I dial up the gap and put different signs on the gap, whenever the gap changes sign, I have the kink states. So I now have 4 channels, right, forming a cross in each way. So that's dual gated area. This is the places where we send contact in. So this is heavily doped. Just work on the back gate. That's dual gated. This is heavily doped. Right? So that's how these things look like optically. And in the top gate, just the 4 gate on top looks like in a SEM image. So the important thing here is now we went all dry. This is all dry transferred. The entire stack of BN, Bilayer Graphene, BN came all on top of the graphite bottom at once. Right? And this is very important. It gives you a cleaner interface. So I'm reducing the states that could possibly live inside the gap and closer to the edge of the gap. Right? Okay. So you asked about alignment. So yes, alignment is very critical, because we need to align this edge with this edge, right? For those of you who do E-beam, you know that if you do it in 2 sessions, they're not going to spontaneously happen. Right? You're off by maybe 30 nanometers, then you don't have your experiment, right? So we go through a special process for that. This was all written up carefully in the supplementary material of that paper. If you want to know more about it, also I can tell you more in detail, right? So ask me later. The end of the day, we could do about 10 nanometer in alignment. And it's also important to control the size of the split. We're doing a lift-off process. We need to know how much that gap is, and we could do that to about 5 nanometers. Right? So it requires some work. But it does work after you go through pain. This is for the students, right? Didn't look like this, it looked like that before, right? So liftoff is challenging. You have so much metal around it. You guys know about these. So, but it can be worked out. Right? So, yeah.
I was wondering, in the case that there is a misalignment, is there a way to distinct, right? So that means that you would have some doping, some strip that gets doped.
Very good, yes. Yes, in fact, you can track how, for example, the charge neutrality point shifts with silicon, and that tells you exactly how much misalignment you have. Right? It cannot be too big, because otherwise you will shift out of registry, and then no experiment either. Right? Right. Okay, so one more piece of information before I show you more data. I have a self-built-in control. This is the configuration we're studying, minus plus, kink states, momentum, valley momentum locked, right? That's what those colors, they live here. Now, if I do plus plus, there's no kink states, no band inversion. So I just have a gapped area, reduced gap, right? Okay, so I can compare the 2 situations by changing the Fermi level and ask what is the conductance in this case versus the conductance in that case. In this case, it's a high, ideally 4a squared over h. In this case, low, ideally 0. But I can look at those. And lo and behold, that's the first experiment we did, which is to compare the conductance in those 2 cases. And exactly in these 2 cases, these 2 bands we call even gating, resistance is high. In these 2 cases, the resistance is low. So we know the kink states are there. They're not quantized at this stage yet. If you have good eyes, you can see that there's some resistance there. They have maybe a mean free path of about 100 nanometer or so. Okay? It's in these later devices that we get it up to about 3-4 microns. Okay? So Professor Hu Jun Lee's group also did a similar experiment without the Fermi level tuning and roughly see a similar phenomenon there. Right? Okay, so that's our first generation. All right, so I'm gonna tell you a bit about what the second generation device looks like, how we operate it, and very briefly these valleytronic operations that I mentioned. Right? So this is the cross, right, that we have. We can measure each channel individually by just heavily dope the other side. And we can measure this channel. We can take that measurement, walk 4 times around, understand what each part does. We can also send a current from here in and have 3 amplifiers sitting on 2, 3, and 4 and ask which one gets the current. So that's the splitting operations there, right? Okay, so that is that. All right, one more piece of information, right? So you will see me using magnetic field. We first do experiments in finite field, then we go back to zero. What magnetic field does is two things. Number one, it forms lambda level, so it makes this natural band gap at B equals 0 larger, makes it larger, it helps. Number two is it makes lambda levels in the conduction and valence band of those blue states that I showed you before. Right? So you will see lambda levels here, lambda levels here. Those are quantum Hall effect, the chiral edge states that I mentioned. In between the states that live inside the band gap, that's the Kink states. Right? Bilayer graphene doesn't have such states at nu equals 0. So this reason it comes about is because of this inverted band structure that I just spoke you about. Right? Okay, so we're expecting h/4e square of resistance inside the gap. And when I cross an edge, I get another 4. When I cross another edge, I get another 4e squared over h, the same thing in the valence band. So as we sweep the Fermi level, you see the resistance of one channel go through a step. Right? Okay. The difference between those two plateaus is exactly between 1/4 and 1/8 h/e squared. This is living inside here, and this guy is cutting across here. So here's another device. You can see now more, 12, 8, gap, 8 again. Here's all of them are lifted. If you have good eyes, you'd realize this is not 6.5 kilo ohms. It's more than that. Every one of them has the same contact resistance added on top of that because we're doing a two-terminal measurement. Right? That's how we figure it out because it's the same thing on every plateau. So that's another device, right, which looks like so. Okay, so this shape over here actually comes from this area, this area. We know that from other measurements. When it's flat, then we get a very good plateau. In fact, it is a plateau that extends over a fairly large gauge range. Right? Okay, so that is the signature of the Kink states.
How long is the channel?
Channel is 300 nanometers. So then I dialed down the magnetic field. That was a finite magnetic field. You see that's 8, 4, 6, 4, 2. By the time you go down to 0, the resistance actually came down. You cannot be more conducting than the ballistic conduction, not in this case. So the reason that the resistance came down is we turned down some other conduction channel. And that conduction channel comes from leaking through the dual-gated region, so some parallel conduction passes didn't show very well the color there. We know that because we can separately measure it by doing plus plus. And you can see that at B equals 0, it's quite appreciable. But as you crank up the magnetic field, this becomes very quickly very insulating. When the parallel channel goes insulating, we get back our conductance plateau. So using these measurements, we can go back and just do a two-channel model and figure out what is the resistance of our Kink states. So it's about 7 kilo ohms at B equals 0, and then it becomes quantized at a few Tesla or so. So I'm overlaying 3 devices here, so you can see that they more or less do roughly the same thing. Mean free path estimated about 3-4 microns also. It could be better if we could apply a larger gate voltage to open up the gap even more. We couldn't in these devices. This is one of the gate is a little bit weak and it leaks earlier, right? We have 9 of them, so one of them kills you in some way. So that's the direction to go, to make the gap even larger and to make the transfer even cleaner so that we don't have anything inside the band gap at all. Right? So that's something. We already have this advantage of defect-free. We need to work on number 2 and number 3 there. Right? So that's our path to even better conduction. Right? Okay. So I think I have maybe about 10 minutes because you guys came in late. Okay, all right. So I'm going to briefly show you how we do valleytronics. Right? So that's in this kind of configuration. Okay. All right. So the basis behind that is, well, there are two ways of creating states, right? Minus plus or plus minus. You take this, and you grab it and turn it 180 degrees. You now have that, right? Cannot do that with the quantum spin core insulators. It's given by nature. Here we're creating it with the electric field. So I can do this, I can do this. Right? So in the same valley, you can see my states changed its propagation direction. Or in the same propagation direction, now it corresponds to a different valley, right? This is fun if you put two of them together. Either you can line them up like that, or you can make the opposite helicity, like so. Right? In this case, I align all of the indices, right? Propagation and valley, all aligned. So it's a straight waveguide going through. In this case, if my electrons going up, they have to go from K to K prime. And if I suppress K to K prime scattering, do a good job on that, this is going to shut off. So that's the off state of the valley valve. Okay? It is a little bit similar to spin valve because spin valve also uses this alignment to control on and off. But it is different in the sense that for a spin valve, you need to have spin polarized current to start, right? So here, my current coming in is almost 50-50. It's K prime almost not polarized. But lo and behold, there is a valve in K, and there is a valve in K prime. This is where topology comes in. Because I did the valley momentum locking, I have a valve mechanism in both valleys without creating any net valley polarization. So that's how this scheme works. And it actually does work. But I'll show you a simulation first. This is my colleague Ivar Martin's wave packet propagation simulation. You can see the straight waveguide. You can see in this case, although it doesn't go forward, it has two ways to go. It can go left, just follow the arrow. It could go right, right? Okay, so that's a 50-50 beam splitter, right? Okay, if you don't break any other symmetries, that's what you're going to get, a 50-50 beam splitter. But there is one other knob which we can do to control this splitting, and that is magnetic field. Because magnetic field differentiates left and right, right? Right. So this is something that I'll show you in a second how we do that. Right? So the waveguide operations. So this is the one channel up here. This is the south channel down here. And this is if I measure through both of them. You can see that these three curves overlap, including the wiggles. The wiggles come from this area over here, right? So 4e squared over h plus 4e squared over h, we still get 4e squared over h. It's only one situation, which is your wave packet just propagated through ballistically, right? Okay, so that's a waveguide. We can actually guide it making a turn, right? You can guide where you put the state. Whenever you have the same sign, there's no state. So if IBM can cover the wafer, you can channel your electrons around on the wafer, basically by flipping gate voltages, right? So we just did a right turn, and we did a left turn. It works. So more interestingly is this valve configuration. Right? So I'm sending current in here. I'm draining it at all three terminals simultaneously. And you're looking at the current that's received by each terminal. So the red one, and I'm sweeping Fermi level. Red one is what this one gets, the north. Notice that it's always very low. Right? That's the valve working. It's not supposed to get any current in an ideal case. Right? Gets a few percent. Notice that this terminal and this terminal formed an X. That's really the beam splitting. Why? At the charge neutrality point, it's a 50-50. by the time you're deeply electron, this guy is getting all the current. When you're deeply hole, that one is getting all of the current, right? I had made a tunable beam splitter in this case. So this valley blocking effect comes from that we did a reasonably good job suppressing K to K prime scattering. Okay?
I got a little confused.
Yeah.
What if I just kind of flip the magnetic field? Do I get the same signal or the signal back?
The signal reverses.
With the opposite magnetic field?
Yeah.
Is that-
Because you will see.
I fixed the same polarity in terms of the bias.
Yeah, and it reverses because the Lorentz force changes direction. I'll show you the diagrams, right? In fact, we did all sorts of things. There's a sort of like an Onsag relation you can work out for this.
Here comes my kind of confusion. Because
Yeah.
I thought kind of you turn on the magnetic field to help just the kind of gap increases, but all the chirality is basically set by the electric field you apply. Right?
You will see how magnetic field, it does one more thing that I'll show you, right? And that relates to the question of which way it goes, right? Okay. So we have a on-off ratio of 800%, just to make the number look larger, 800%. At B equals 0, right, at 1.7 Kelvin. Pretty long way to go towards a real device, but we're happy to do some physics with this. Right? So Valley valve works down all the way to B equals 0. The splitting does not work when you turn down to 0 because the splitting relies on the magnetic field. And the reason it does so is because it's controlling the wave function, and that's what Philip is asking. So this is calculations by my colleague Zhenhua Qiao and also Francois Peters. As you change, so Lorentz force is here. Remember, K and K prime have opposite group velocities. So they experience opposite Lorentz force, right? Okay. So the wave packet, K and K prime split as you turn on field. It splits more as you go up in Fermi level. That's what the calculation said, right? Okay. So at the charge neutrality point, there's a symmetry. They always overlap. So they always look like so. As you go to a more electron deep regime, you see they start to look more and more like quantum Hall edge states. By the time they fully separate, they really do look like chiral states, right? So now if you send the electron in, let's say your excess current is carried by K, it could only turn right. It cannot go to the left because there's no wave function overlap. And that's the thing we're tuning with EF and B. If you go to the whole regime, you can see that this one now moves towards the left. So that electron would now go to the left. If you flip magnetic field, everything else flips. Right? Right. So that is the splitting. Yes?
If you did monolayer graphene in this sort of geometry, would the magnetic field do the same thing?
You can't create this in monolayer graphene. You have to break the sublattice inversion symmetry, right, to create a gap to start.
So this isn't just a quantum.
No, it's not. So it's the chirality built on top of the kink states. So beam splitters, right, okay, if you do optics, you do that, very easy. You get your crystal inserted. It's very useful because you can create entanglement by bringing things together and so on and so forth, right? When it comes to electrons, it's not so easy. Right? So electron, good beam splitters for solid state electrons. Someone is smiling there. This is from Marty Heibloom's group back before you joined, I guess. Right, so this is a Mach-Zander interferometer. We're looking at beam splitter of quantum Hall edge states that come from a quantum point contact. Right? Not so easy to make. So we just made one for our system. It doesn't look like this. It looks like a cross, but it works like a beam splitter. Right? And we're trying to make that down to 0, B equals 0, by changing the size of the gap. That's another way of controlling which way the wave function pushes, right? So this requires a field. This doesn't require a field. Right? That's something that we're working on. I'm going to skip theory. The only thing I would say is that Chaoxing Liu is a wonderful colleague, and all that we see can be understood quite well if you put S-matrix transmission and Landau or Buttiker together. So it really tells you that we're doing edge state transport. You're looking at one-dimensional systems there. It turns out that you can make these quantum valley Hall Kink states in more than one ways. We made it for electrons. There are other people who are making it for photons. That's my colleague Mikhail Reshman's work. They're looking at the wavelengths of 1.5 micron photonic systems. These guys made it for microwaves. You're looking at 12 millimeters. You can kind of see some of the schemes that I'm talking here, right? So I forgot one of them is theory. The more beautiful one is theory, and then one of them is experiment. But you kind of see this splitting action going on, right? And somebody made it for like metal plates and crystals. This is millimeter, centimeter scale, right? Sonic crystals and so on, right? So from a nanometer to centimeter, one could utilize that symmetry to create these kind of waveguides. They're all waveguides. They're waveguides guiding waves of different wavelengths. Okay, well, I think I have said a lot. I hope that you liked the thing we created. This is a Valley helical system called the Kink states. We made it out of Bilayer Graphene. We electrically defined them and electrically controlled the transmission of it. Right? There's a somewhat amusing YouTube video that made a little animation of this color scheme that I talked before, how the traffic control happened, right? So if you're interested, take a look. We're doing work to make the sample cleaner. Right? We want to be ballistic. We want to be clean enough to do other interesting experiments. And some of the interesting experiments are, for example, if you couple it to superconductor, what happens? You have a helical system. You have to couple it to a superconductor, right? If you have a helical system, you couple them to a superconductor, right? So counter-propagating states. I'm sure you all appreciate that statement, some of you at least. Right? This cross gives you a way of letting two branches interact. So we can think about interacting, using that to probe is there a Luttinger liquid behavior in the system that's different from other systems. The theory says it does. It has interesting phases. Right? So that's something that we're looking at. Right? Maybe, I don't know, some company would say, oh, yeah, this is good enough. Let's cover the wafer with it. And then it's actually much easier to do all of this with optical lithography. If you think about how the silicon industry controls the precision of lithography, it beats us by orders of magnitude, right? They're doing 7 nanometer nodes. How much misalignment do you think they have in their system? Very, very little, right? So by the time you scale up, it actually becomes easier in terms of operating. So I don't know, maybe it will become a kind of wire that could wire up the quantum computer that you're working with. I don't know. We'll see what happens. Well, that's about all I have to say. This guy is my hero is Dr. Jing Li, who is now a director's fellow at Los Alamos. He did all the experiments, and collaborators at USTC, Professor Zhenhua Qiao's group, Professor Chao-Xin Liu's group at Penn State, and these two wonderful gentlemen that appear on all the graphene papers, that if they decide not to do this anymore, we are all just going to go home, right? I don't know. And thanks a lot for your attention.
Is that just an incidental?
No, I'm glad you asked. I can talk for another half an hour, but I won't. But you have good eyes, so I'll show you what that is. That actually gets more pronounced as you go to larger magnetic field. And I want to find that slide. So you remember the Kink states are fourfold degenerate, right? Right. So when you turn on a magnetic field, this actually splits. The bulk splits, the bulk lambda level splits. These are also the split, right? It's a guiding center picture. So instead of 4 pairs, you now have something look like so. And as you ramp through, you're ramping through these different modes. And if you work through, this is all in the supplementary material of that science paper. There's an entire paper within the supplementary material talking about the high field behavior. You can, in fact, come up with explanations on why this happens. In the end of the day, as you crank up field, these fractions, or quarter and half and quarter and so on, are basically due to those quantized modes. So 1/4 meaning 1 mode goes one way, 3 modes go the other way. Right. Right.
So you mentioned that when you put the chemical potential right at the Dirac point, when you turn on field, there's no spatial separation of K and K prime because of the symmetry. So at that point, basically at low fields, there's still a bit of Valley scattering, right? Because it's not exact on that. Is there a way to come up with a number, that number of the gap, let's say, between K and K prime when the chemical potential is direct? Because as you mentioned,
Is there a way to come up with a number for the gap?
Yeah. So basically, there's a helical state. Like you mentioned, everyone wants to put a superconductor. Of course, the superconducting gap should be larger than this gap.
Right.
Otherwise, it's not you cannot access topological properties. So
Why does your superconducting gap have to be larger than that?
So basically, there is scattering of K and K prime.
Right.
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 So this corresponds to a gap. Right.
Nope.
I mean, there's tunneling.
Okay. So this is my gap,
Yeah,
right?
So
Okay.
let's draw the minus K also at the same point because they're in the same position, right?
Yes. So that's why I just draw 2 of them here. Yeah.
So one is up, one is yeah. Exactly.
Okay.
So now there's Valley scattering, right? Tiny bit.
Yes. I think it's mediated by, for example, a puddle inside this gap, higher order process. It's not because we have an atomic defect that goes from here to here. But go on, yeah.
I mean, there is tunneling, right?
Right,
So
yeah.
That tunneling must correspond to a gap, right? So what is that gap?
I don't know if I would think about it that way. There is a scattering, but it doesn't mean that it would open a gap.
We can discuss later. Yeah. You already asked questions anyway.
I see, now there's a quota system.
Too long, so okay. Let's thank the speaker once more then.
Thank you.
What's the speakers?